Okay, so today, last time we met, we covered topics in chemical reactions. And today we're going to look a little deeper at reactions in aqueous solutions. In chapter 6, we finished off, I believe, with balancing equations. Yes, balancing equations. So hopefully you've had at least a little bit of practice with some of those review problems. And we're going to continue with balancing equations, but we're going to get into another topic now called stoichiometry. And we're going to be able to, excuse me, determine with a balanced equation, if we're given a certain amount of reactants, we're going to be able to determine how much product we should expect to see. All right. So let's get on with it. First, when we're describing a chemical reaction, it's useful to have an idea of whether we expect that reaction to actually occur. There are many combinations of reactants that will not react. They won't produce products at all. And some of them, when you put the reactants together, they need a little kick to get started. If you turn on a Bunsen burner, you've got natural gas coming through the burner and mixing with air, but you just hear a whish, right? A whooshing sound and no flame. What you have to do is give it a kick, hit it with a spark or with an open flame, and it'll light. So let's take a look at some of these things that help us predict whether a reaction is going. We refer to these terms as driving forces. What drives a chemical reaction to occur? And there are four basic ones. We observe is the formation of a solid. If a solid forms, if you have, let's say, a cation and an anion in aqueous solution, and then you have another cation and an anion in aqueous solution, right? They're both soluble, and then you put those two solutions together. The possibility is for that cation to associate with this anion. So there would be a Cb and an Ad possibility. Okay. Maybe this one stays in solution, right? Which another way of putting that is the ions are still free floating. They're not associated. But suppose these two ions do strongly associate with one another and they are no longer soluble. Then we call that a solid or a precipitate, and it drops out of solution. So what does that effectively do for the reaction? If this one drops out, then we're removing this product from the reaction mechanism, from this description. And when you do that, it's kind of like a pull. You're pulling from this side and you're driving the reaction that way when you remove that solid from the solution. If you do, then it's no longer available for any other types of reactions. Chemical reactions typically will go both directions. They'll go forwards and backwards. So if you remove, and this happens to a greater or lesser extent, sometimes they go more to the right than they do to the left, or they're more to the left than they do to the right, but usually they will go both directions. And if we move the solid and take the solid out of the reaction environment, now it can't go backwards. The only reaction available to it is forwards. So that drives the reaction to the right. Another possibility is the formation of water. So when we have pure water, looks like this, H2O, right? Everybody knows that. But pure water has the capability of undergoing a reaction of its own. It will dissociate. Into these two ions, right? So 1 plus and 1 minus is neutral. That's neutral. So we're balancing our charges. The interesting part about this is it only happens to a very, very, very small amount. So the reaction, the principal reaction is in this direction. Right? So if in the reaction you have available hydrogen ions and hydroxyl ions, they will associate like this and make water. And if they do, they effectively remove those ions from the environment and drive the reaction toward producing more of those ions. For instance, let's say we have hydrochloric acid, and we put that together with a solution of sodium hydroxide. Okay, so what should we expect? Well, this sodium could associate with that chlorine, right? But we know it's soluble. So there's really no reaction there because the ions are still independent from one another. But this hydrogen ion here and this hydroxyl ion here get together and they make water. That drives the reaction this way because those two ions, the hydrogen ion and the hydroxyl ion, really want to be together. They want to go over here and be that. So it drives the reaction toward water. Transferring electrons will also drive a reaction. So if we have a pure metal like sodium, and we put it together with chlorine gas. Now, if we just put them together like that, nothing much is going to happen. Well, not right away. But eventually what they want to do is get together and make sodium chloride solid. Okay, this is neutral, that's neutral. One thing you'll notice is that equation is not balanced, right? You've got two chlorines here and only one chlorine there. So first thing we need to do is balance the equation. So we need two chlorines. Now we need two sodiums. Okay, so now it's balanced. Well, how did it get from here to here? Well, there's no charge on the chlorine, right? Remember, the upper right-hand corner is for charges when we write our symbols. There's no charge here, and there's no charge here. Those are pure elements. But that compound is composed of ions, this positive ion and this negative ion. Right? How did they get there? Well, they got there by transferring electrons. If we transfer electrons from sodium to chlorine, let's see, sodium loses electrons. In fact, it loses 2 electrons. And chlorine gains electrons. So it gains 1 electron for each chlorine. Now we've got an extra electron for the chlorine here. And sodium is deficient in electrons. It's positive charge because we withdrew electrons from it. That transfer of electrons effectively drives the reaction. Formation of a gas. Okay. That's one other way that we can drive a reaction. So let's say we have hydrochloric acid and we drop a chunk of zinc in it. Zinc metal. What's going to happen? Well, actually we get transfer of electrons for this too, but we're focusing on the formation of a gas. So here's what happens. That zinc becomes a positive ion. In fact, it becomes two positive ions. Okay? Two chlorines accept electrons from the zinc. So now the zinc has a 2+ charge and the chlorine has a -1 charge. What's left over? Hydrogen. Those two hydrogens get together and they form hydrogen gas. Okay? Now remember, like I said before, reactions can go in reverse if the conditions are right. So when these react, producing that gas escapes the reaction environment. Now it's no longer available to go backwards. So the reaction is driven to the right to try to replace some of that hydrogen. And it just keeps disappearing. So the reaction goes to the right until either all of the zinc is used up or all of the hydrochloric acid is used up. And then it has to stop, right? No more reactants. It's got to stop. So those are the driving forces, typical driving forces for reactions. Formation of a solid, formation of water, transfer of electrons, formation of a gas. And sometimes these occur in combination. All right. Let's watch this little video. And it's a discussion of one of the driving forces, formation of a solid.
So in the reactions we've seen so far then, we mix chemicals together and we know that a reaction has taken place because we get a change of colour. But there are lots of other ways that a chemical reaction can show up. And one way is called a change of state. So the state of something just means whether it's a solid or liquid or gas. So if something turns from a solid to a liquid or from a gas to a solid, then it's changed state. So let me show you an example of a chemical reaction that involves a change of state. So I'm going to use these two liquids. I have a red liquid and a colourless liquid. What I'm going to do is to pour the colourless liquid onto the red liquid very carefully and try to make two layers. So what I want to happen is for the colourless liquid to be floating on top of the red liquid in separate layers so that they don't mix. Okay, so I think that's worked quite well. So what I've got now is one liquid floating on top of another, and where they meet, they undergo a chemical reaction. And they're actually making a solid. A solid material is formed where the two liquids meet. And what I can do is to fetch out some of this solid material. And as I pull it out of the beaker, of course, it allows the two liquids to meet each other again, and so they react again to form more of this solid. So if I'm careful, so as I wind, I'm pulling up this material, and it allows the two liquids to meet again, and it forms more of this material. And this substance that's being formed is actually nylon. So we're making nylon as I speak. And if I'm careful, I'd be able to just keep on turning this and making this long thread of nylon, at least until we run out of solutions. Okay, so that's an example then of a chemical reaction that involves a change of state. So let's have a look at another reaction that involves a change of state. And for this, I'd like a volunteer, please. Who would like to volunteer? You're very keen. Come on down. Let's have a big hand for our volunteer. You would like to stand there. Let's pop those on. What's your name?
Dylan.
Dylan. All right, Dylan, if you stand just there, we're going to do some chemistry and we're going to make a solid. All right, I'm going to start off with a flask that contains a solution of silver nitrate, and I'm going to add a little bit of ammonia. Now, when I add the ammonia, you see that it's forming a sort of brown colour. I'm going to keep on adding the ammonia, and in a minute that brown colour should disappear. There we are, it's disappeared, isn't it? Now what I'm going to do is to add some sodium hydroxide. That's now formed a sort of very dark brown, almost a black material. So I'm now going to add more ammonia. And again, I'm going to add ammonia until the liquid goes back to being colourless. This takes a moment or two. There we go. And then finally, I'm going to add some glucose. So there's the glucose. Now I'm going to put the lid on, put a clip on. I'm going to give it to you, Dylan, and I want you to hold that, and I want you to give it a really good shake. That's it, really hard shake, that's good. That's it, keep shaking. That's it. So what's happening inside this flask now is there is a chemical reaction taking place, and it's forming a solid. And the actual material that it's forming is silver. We're making pure silver metal. Keep shaking. It takes about 3/4 of an hour, is that okay? It does actually take a minute or two, but the harder you shake, the better it works, so keep shaking. Don't drop it though, okay. So metal, silver metal is being formed sort of atom by atom, and you can see it's all going quite black. That's because very finely divided silver is actually black in colour. What we're hoping is going to happen over the next minute or so is that those particles of silver will start to stick to the walls of the flask. And as they build up, we should see silver metal, and in the form of a mirror, building up on the inside of the flask. And you're all seeing those sort of decorations that you get at Christmas, those spheres that are shiny, and they're made using this chemical reaction. The little balls of glass, and the inside is coated with silver using this kind of chemistry. Doing really well. Okay, let's have a quick look. Almost there, keep going a little bit longer. Still looking a little bit dark. Excellent. All right, give it back to me then. Right, so I'm going to take the clip off, take out the stopper, just wash that off, and I'm going to pour out the remaining chemicals, and then I'm going to rinse this out with distilled water. I'm going to rinse it out a second time. Rinse it out a third time. There we go. And I'm just going to put that on, just dry this off, and put the clip back on. And if you'd like to just give that a little polish, there we go. If you'd like to hold it up by the neck, that's it. And if we bring a camera in and have a look at this, and we've got a lovely silver mirror. There we go. I'll just stand there. Okay, what I'm going to do is give that to you as a souvenir to take home, and you can go back to your seat. Let's have a hand for a volunteer. Okay, so that's an example of a chemical reaction that produces a change of state. I want to show you another example of a chemical reaction. Again, this is going to go from being a liquid to being a solid. So in this flask I have a solution of sodium acetate. And this sodium acetate's a liquid, as you can see, but it would very much like to be a solid. It would like to turn into a crystal. But it needs a sort of an excuse to get going. And the excuse is going to be some little crystals of solid sodium acetate in this dish. So watch what happens as I pour the liquid onto the crystals. So I think you can see there the liquid, as soon as it touches the crystals, is turning into a solid. And with a bit of luck, we can make a sort of chemical sculpture. Seems to be working. Okay, so that's a sort of sodium acetate sculpture. Now, oddly enough, this actually has a practical application, and this is the practical application. This is something called a hand warmer. And it's a plastic pouch, and it contains exactly the same liquid as in this flask. It's a solution of sodium acetate, and it would like to turn into a solid, would like to turn into a crystal, but it needs an excuse to get going. And the excuse is this little metal disc, and if I just flip this disc backwards and forwards, that should be enough just to start the crystallization off, and there it is. And we can see the liquid turning into a solid. And as it does so, it's actually getting warm. So it's actually giving off heat. And there it is, it's turned entirely into crystals. It's become quite warm in the process. I can put that inside my glove and keep my hands warm for half an hour or so. And then I can take this and put it into boiling water for a couple of minutes. The crystals will turn back into a liquid. I can allow it to cool and they'll stay as a liquid. And it'll stay like that for weeks or months until I'm ready to use it again. I can use it thousands of times. Okay, so that's sodium acetate, a sort of chemical sculpture. I'm going to show you now another way to make a chemical sculpture. And Chris has been preparing this. This beaker contains a mixture of para-nitroacetanilide and sulfuric acid. And Chris has been warming it up. And when it's hot enough, it will undergo a reaction in which this liquid will turn into a solid. This makes quite a bit of smoke, so we've got this special hood that will suck away the smoke from the reaction. Okay, here it goes. Okay, so that's a chemical reaction that involves a change of state. So
Okay. That was pretty interesting. Those reactions were driven to completion by a change of state. Here we have another example of a change of state where we form a precipitate. We put two solutions together and they form a solid by a reaction that I described in general terms a little earlier. The solid is called a precipitate. And if you let it sit long enough after the solid forms, it will settle out of the solution. It will separate. I've got a video coming up. I think it's next. Yes.
What I have here is two Erlenmeyer flasks. One has lead nitrate solids in the bottom, and one has potassium iodide solid, or salts on the bottom. I'm going to make solution, an aqueous solution with these. So I'm going to make aqueous lead nitrate here. Mixing, you can see that it makes a solution. And it does dissolve. It is definitely aqueous. And same thing with the potassium iodide. Hopefully I don't make as much of a mess. This is the Ki, adding some water. Also making an aqueous solution. And both of these solutions, or both of these salts, are soluble in water. So as I stir, and I have two aqueous solutions. You can see through them, and you can see the solids are now been dissolved. Okay. Now, interesting enough, lead nitrate is made of the nitrate ion. The nitrate ion is NO3-1, and anything combined with a nitrate ion is soluble because the nitrate ion, NO3, is 4 atoms stretched, and you have a negative 1 stretched over 4 atoms, so its charge density is very low. So it doesn't attract other ions in a crystal as strong as others. So its lattice energy is lower, and it's easy for water to pull apart the ion and have those molecule ion attractions that make this a possibility. Same thing with Ki. You have potassium iodide, and you have Ki ions that are free in this aqueous solution, and the K is +1. The +1 ions are a big ion, and they are spectators for most types of reactions because they have a +1 over a large area as well. And the iodine, like most halides, are also soluble because they're a -1 and they're also a big ion. There's some exceptions with those, and we're going to see that one right here. So I'm going to pour these together and take two aqueous solutions and see if a precipitate results. Now, precipitate is when a solid comes out of the solution, because we're going to do a double replacement, or something called a metathesis reaction. Lead +2 from this beaker is going to attract and hook up with the iodine ion to make PbI2, or lead-2 iodide. And that is going to create a precipitate, because the lead iodine prefers itself more, or attracts itself more, than water. So let's do that. Here we go. Very brilliant reaction. And you see that as pretty, very pretty yellow precipitates. A lot of yellow leads, lead paints have been known to be yellow, and also a problem. So there you go, and there's your precipitate. And it's a precipitate because I know that I cannot see through the solution anymore. And if we let this settle for a while, we'll get something like this. This is a reaction I did about an hour or so ago, and you can see here that the clear solution is the potassium nitrate ions, or the potassium and nitrate ions, and the solids are at the bottom. That's settled at the bottom. All right? So there is your precipitating reaction.
Now, the narrator of this video used a lot of big words like double replacement and metathesis, and he talked about the size of ions and charge density and lattice energy. You don't have to worry about those at all. Just recognize the fact that when you put these two solutions together, they swap partners. The K associates with the nitrate, which is still soluble. So these are independent ions. And the lead and the iodide get together, and they form a precipitate, this yellow colored solid. And I've balanced the equation here so that we know one lead, two nitrates, two potassiums, and two iodines. That balances the equation. All right, we're going to talk about water a little bit. Let's see if I got something up here in the way. Yeah, I'm sure you can't see it, but that's okay. Water is often referred to as the universal solvent. That's not technically true. There are some things that are not soluble in water, and we just saw one, right? This compound is not soluble in water. But water does dissolve many things, and it does serve as a solvent for a host of different solutions. There's a reason for that. Water is a polar molecule. What do we mean by polar? Think of a magnet. A magnet has poles. It has a north pole and a south pole. A bar magnet like that has a north pole and a south pole. And you know, if you bring two magnets together, then if you try to force the north to the north and the south to the south, like this, you'll get a repulsive force. Push it apart. But if you go the other way, if you put the south on this end and the north on that end, you'll get an attractive force, and it'll draw the magnets together. Now, that's not strictly speaking what happens with molecules. Molecules are more electrostatic. And when we talk about that, we mean if you have a positive charge over here and a negative charge over here, then they will attract one another, right? So opposites attract and like charges repel. So I said all that to try to make some sense of what we mean by water as a polar molecule. In order to understand water as a polar molecule, you need to understand something about how it's made. What is its structure? The red ball there is oxygen, and the white balls are hydrogen. So this molecule written that way actually looks like this. We've got an oxygen molecule bonded to an oxygen atom, excuse me, bonded to two hydrogens, and they're bent like that. Now, why does that make a difference? Well, when you get two atoms bonded together, they don't equally attract electrons to one another. Now, these bonds are covalent, that is, they're sharing electrons. So there are two electrons in here, in that bond. But oxygen has a much stronger pull on the electrons than hydrogen does. It's not enough to completely remove electrons from hydrogen to form ions, but it is strong enough to force the electrons to spend more time around the oxygen than they do toward the hydrogen. So we have what we call a dipole on each of these bonds, and we draw it like this. This shows you the positive end, right? So this side is going to be slightly positive, and that's a Greek letter delta with a positive charge. That just means that it's not a complete charge. It's only a partial charge. And we have a partial charge here. Now on this side, we have a negative charge because those electrons are spending more time around the oxygen. So we have an unbalanced electron distribution in this molecule. And when we take everything together, that gives the molecule what we call a dipole moment. It's more negative on this side and more positive on this side. So the end result of that effect is that when two water molecules approach one another, they're going to line up like this. The positives are far away from each other, and the positive and the negative are close, and they form a partial bond. This is not a complete covalent bond, but it's a partial electrostatic attraction, okay? And if there are any other molecules that you want to put in solution that either produce ions or polar molecules, they will be attracted to the water and brought into solution. All right, so there's our artistic representation of the polar nature of the water molecule. So many substances in the environment are polar in nature, or ionic, even ionic in nature. And if they are, then water can dissolve them. Many of them, I should say. Some of them, like our previous example with lead 2 iodide, has a stronger attraction to its own ions. Positive to negative ions is stronger than the attraction to the water molecules. So they cannot pull that association apart, those ions apart, and they drop out as a solid. So there's actually a battle going on between the compounds and the water in that case. And in the case of lead 2 iodide, the compound wins, and it forms a solid that will not be held in solution. Okay. Many ionic substances can be broken apart. Sodium chloride, for instance. If you have a sore throat and you need to gargle salt water, you know what to do. You put a teaspoon of table salt into a glass of warm water, and it goes into solution. and then you gargle it. So what happens when water attacks a crystal of, say, sodium chloride, so you have a crystal of sodium chloride here. And if any of you have ever looked at a crystal of sodium chloride with a magnifying glass, you'll see that it's shaped like a cube. That's because of the way the ions are arranged in that material. So you will have, say, maybe a sodium here, and you'll have a chlorine here, and then a sodium here, and then maybe a chlorine over here, and then a sodium here, and then another chlorine there. And they're in this crystal matrix. The ions are attracting one another. They're very strong attractions. But when water comes in, for the chloride, it will associate the positive side, right? This slightly positive side, right? And form an attraction. Well, other molecules of water will also come in if there's room, and they will form an attraction. But there are other water molecules on this side that are also attracting. So you get this, over time, you get a lot of water molecules associating around these ions, and they're very strongly pulling those ions. And the strength is large enough that it will break the bonds between the sodium and chlorine, or the chloride ions, in the crystal and pull them apart. We call that process hydration. And then once you get them in solution, the positive ions will be surrounded by these positives from the water molecules. And then a similar thing happens to the sodium, only with the sodium, it's associated with the negative side, or the oxygen side of the molecule. That's how we put polar substances or ionic substances into solution. Oh, I have an animation. Here we go. So here we have water molecules that are going to associate with the sodium and pull it apart. And then a similar thing happens to the chloride ions and pulls those apart. And they just keep opening up fresh surfaces of the crystal, and water molecules attack until the entire crystal is dissolved. Okay, so when we put something in solution, say we put whether it's an ionic compound like sodium chloride, or a non-ionic compound like table sugar, right? Both of those will go into solution, aqueous solution, readily. So if we have a container of water and we put sodium chloride in solution, we have all these free ions floating around. Right? Whole billions and billions of them. Well, if you attach a battery to some electrodes and you submerge the electrodes in here, right? And say this one's positive and this one's negative. So it's going to want to transfer charge from the negative to the positive. Well, those electrodes, and remember when you're trying to move a current, electrical current through conductors, you have to complete a circuit. It's got to be complete all the way around. So now that we have ions in between those electrodes, they can transfer the charge from one electrode to another. That circuit is completed. And that's why in this right-hand image, you see the light bulb is lit up. Okay. Now, suppose we have another jar of water, and instead of an ionic compound, we put a non-ionic compound like table sugar or glucose. Glucose is a molecule that is shaped like this, and each one of these is a carbon. Carbon, 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 carbon. Well, on this side, we have like that, and like that, and like that, and like that, and like this. Okay, so notice something about that. Oh, excuse me. Let's see. 1, 2, 3, 4, 5, 6. Okay. What you'll notice is on this molecule, we have lots of OHs. Right? Those OHs act just like the OHs in water. They form a slight difference in charge. So this hydrogen will be slightly positive, and this oxygen will be slightly negative. And that's something for the water molecules themselves to be attracted to. So these sugar molecules, glucose or sucrose is the same way. It's a different molecule, but it acts the same way. Will be attracted to the water molecules and go into solution. You'll have sugar in solution. But the difference between these two is there are no ions here. So it cannot transfer charge. The circuit cannot be completed. So here we have a similar situation with either pure water or sugar in solution will not conduct electricity through that solution, and the light bulb does not light. Okay, so pure water is an insulator. It will not conduct electricity unless you put something into it that will transfer charge. Okay. Now we have definition. If we put something in solution that will transfer charge, that will complete the circuit, we call that an electrolyte. That's an electrolyte. Strong electrolytes are those substances that completely break apart into their ions. Right, so the strong electrolytes, example is sodium chloride. So sodium chloride in solution breaks up into all ions, goes all the way. A weak electrolyte, on the other hand, is a substance that only partially produces ions. It's still in solution, right? The molecules are still in solution, but they don't break apart into many ions, only a few ions. A perfect example of that is vinegar, formed from acetic acid. Acetic acid is a molecule that's written like this, C2H3O2, and when we put it in solution, it will partially dissociate into those ions, positive and negative ions. Not very much, right? This particular reaction wants to go way, way, way this direction. It only produces a few of those ions. That makes it a weak electrolyte. Okay. So here's another example of what can happen if you have ions free floating in solution. We have potassium chromate on this side, and we have this solution is barium nitrate. And remember that previous video where potassium nitrate was used. All nitrates are soluble, all of them. So this barium nitrate is in solution. And all alkali metals compounds are also soluble. So this potassium is from that first column in the periodic table. It's an alkali metal, and it forms this compound with chromate ion, and it is soluble. So both of these are soluble when they're separated. So what happens when we put them together? Let's see, is he going to show us? Yes. When we put them together, these independent ions, the potassium ions, the barium ions, the nitrate ions, and the chromate ions are now able to interact. They are in the same environment. And you have possibilities, right? So we had potassium chromate was soluble, right? So here's your potassium chromate soluble, and the barium nitrate was soluble. Here's barium nitrate. So there's still some of that around. But if we get the potassium together with the nitrate, it's still soluble, right? No problem there. Nitrates and alkali metals together, they're always soluble. But now we have the barium ions free floating and the chromate ions free floating. And when they encounter one another, they form a strong attraction to one another. So strong that they cannot be dissolved in water. So they form a precipitate. Okay. So you get the combination of these ions, and the barium and the chromate attract one another and form barium chromate solid. It's a precipitate. Okay. So what we're leading up to now is, can we decide if we're given two solutions with salts, different types of salts, cations and anions in each one are soluble, can we predict whether or not a precipitate will form when you mix them together? That's where we're headed. Okay. And that's where that handout I gave you comes in. Let's see if I got a copy here handy. I showed it to you last Tuesday, but let me see if I got another copy of it. I can pull it out. Okay, there's one there. See if I have an independent copy. No, I don't. Okay, so let me pull this one out. This is your review document. Okay, so it looks like that. Let's see, put it in front of the camera. That's your review document. And at the back of the review document, like always, we have useful information. Okay, one of those pages looks like this. Right? There's a chart. That chart has anions down this side and cations across the top. And if you follow the cation down to where the anion meets it and look at the square or the rectangle, if it's clear, then the association of that cation with that anion will be soluble in water. But if, on the other hand, the square is grayed out, then the association of that cation with that anion will not be soluble. It will be insoluble. Right? This chart is based upon some rules, and the rules are recorded down here at the bottom. Now, the reason I give you this chart is because at this level, right, I'm not trying to make chemists out of everybody, but if you were headed for a career in chemistry, you would learn those rules. Then you wouldn't need the chart. But as it is, I've given you this chart. So if you have to make a decision on solubility, then you go to the chart and compare the two, the cation with the anion, and see if it's soluble. Just learn how to use that chart. It will be available for the exam, right? In useful information like all the other exams before it. All right. So these are the rules. We said earlier, all nitrates are soluble. That's true. All salts of sodium and potassium are soluble. Those are alkaline metals. And all ammonium salts are soluble. So this polyatomic ion associated with any other anion will be soluble. Now notice we're ordering them 1, 2, 3, 4, 5. If you find yourself in a situation where you've got rule number 2, say, and rule number 5, both of them apply. The one that takes precedence is the one above, the smaller numbered one, right? If you use the rules. If you use the chart, then you don't need the rules. All chloride salts are soluble except for silver chloride, lead 2 chloride, and mercury 1 chloride. Most sulfate salts are soluble except for barium sulfate, lead 2 sulfate, and calcium sulfate. If you've ever had an X-ray where you had to swallow this nasty stuff right before you go into the X-ray room, this is a barium swallow. They use barium sulfate because it's not soluble. So when you drink it, it will not send sulfate ions and barium ions into your system and cause toxicity problems. It stays insoluble through your GI tract, and they can X-ray it, and it brings out better contrast. You can also get barium sulfate through the other end too, right? You can have a barium enema, and they'll take pictures of your colon. Okay. Most hydroxides are only slightly soluble, except for sodium hydroxide, potassium hydroxide, right? So here we have two rules, 5 and 2, sodium salts, potassium salts. Whereas this rule says hydroxides are only slightly soluble, or we might consider them insoluble. But comparing rule 5 and rule 2 means rule 2 wins. So potassium and sodium hydroxide are soluble. Barium hydroxide and calcium hydroxide are only moderately soluble. Now we're not at this point going to draw a distinction between soluble and insoluble. There are gradations between the two, right? Slightly soluble or moderately soluble. We're just going to say soluble or not soluble. I just want you to understand that there is a continuum, a spectrum of solubility. And then we have these others that are insoluble or slightly soluble. All right. And they all have a bearing on whether or not this chart tells you it's soluble or not soluble. Okay. So we can predict precipitates as long as we match up ions that we put into solution. This is how we would do it. You write the reactants, balance their formulas correctly, and then, since they are soluble, you would write them as separate ions. And then you consider all possibilities of cations with anions. And then you look at your chart to see if they're soluble. Of course, if you have two solutions of ionic substances, you know they're soluble already. So you don't have to waste time on those associations. You want to look at the associations where cations from this solution and anions from this solution get together, or anions from this solution and cations from this solution get together. Those are the ones you want to compare and look them up in your chart. That way you can tell if you're going to form a precipitate. If you don't form a precipitate, then you don't have a reaction. You can't consider that a chemical reaction. It's just another mixture, a solution. Okay, so let's try this one on for size. Can we predict solubility for this example? Okay, so which of the following ions form compounds with lead 2+ that are generally soluble in water? Right? How about lead 2+ and sulfur 2-? Look it up in your chart. And you find that lead 2 sulfide is not soluble. You find that lead 2 chloride is not soluble. You find that lead 2 nitrate is soluble based on your chart or based upon the rule. Rule number 1, all nitrates are soluble. Lead 2 sulfate is not soluble, right? And then we threw this one in there just to see if you're watching. You don't form a compound with a cation and a cation, right? So E is impossible on any level, right? That's the only one that's soluble out of these possibilities. All right. Let's more complicated now. Sodium phosphate. Right? So you need to be able to write that compound from the name. That's why we spent so much time on nomenclature. Sodium phosphate. This has a 3- charge. This is a 1+ charge. So that will be 3. Okay. This is soluble. And we're going to mix it together with lead 2 nitrate. Lead 2+ because it says so in the name. And nitrate. So we need 2 of these. All right, now we can remove the charges. They don't have to be there. And this is soluble. All right. So what's that going to produce? Well, let's see. Let's swap partners. Let's take the sodium and combine it with the nitrate. Right? A -1 and a +1. We look it up. Right? Either sodium salts are all soluble, nitrate salts are all soluble, so we know this one is soluble. Or you can look it up in the chart. Okay. Then combine lead and phosphate. So this is a 2+ charge, and this is a 3- charge. Right? So how do you balance that? Cross multiply. 3 comes over here, and the 2 goes over there. And this one forms a solid. All you have to do is look it up in that chart, and you find it forms a solid. Now, that equation is not balanced yet. But the question was, what is the precipitate? Right? These are your choices. And the choice that we find is this one right here. Lead 2 phosphate. That's the precipitate. All right. Suppose we only give you a mixture of ions, right? Can you tell which ones will form a solid? In this case, it's useful to form a chart, right? We'll do like the chart, the solubility chart, and put the cations across the top and the anions down the left-hand side. Okay. So we have a chart here. And down the left-hand side, we want the anions. Nitrate is one. Let's see, we come to chloride is another one. Any more? Sulfate and phosphate. Right? Those are our anions. Now, across the top of the cations, lead 2+. And what else? Potassium and silver. Okay. Now we can associate. All right. Potassium nitrate. All potassium salts are soluble, right? So these will form aqueous solutions. Okay. How about nitrates? All nitrates are soluble. Okay. Some chlorides are soluble, but in this case, this forms a solid, and that forms a solid. This forms a solid. This one forms a solid. This one forms a solid, and this one forms a solid, I think. Let me check. It says 6 different solids form. Okay, I've got 1, 2, 3, 4, 5, 6. Those are the solids that form. Now, I happen to know that, but you can look it up in your chart. Just cross the cations and anions and find if they're soluble. Simple as that. Let's see. Yep, all the silvers. Okay, just checking myself. Okay, we have when you write out the equation like this, remember, it's the same as always. First, you write the compounds correctly. Then you determine, are they soluble? Then you balance the equation. And in this case, we've balanced the equation as separate compounds, like that. Okay. That's called the molecular equation, or the complete equation. No, the complete formula equation. That would be a better choice of words, because these are not molecules. These are ions, separate ions that associate with one another. Okay, but this term is sort of grandfathered in. The molecular equation is the whole compound equations. Okay. Now, what's actually happening in that solution? Well, in aqueous solution, you've got individual potassium ions, individual chromate ions, individual barium ions, and individual nitrate ions that are in circulation, right? This one on the product side forms a solid, right? So it's not separate ions, it's an ionic solid. Whereas this product is also still individual ions, potassium ions and nitrate ions. So we could write a complete ionic equation for this one. All we would have to do is, after we've balanced the equation, separate the ions and write them separately in aqueous solution. So that's what this has done. We've taken, notice that we had in the balanced equation, we had 2 potassiums in that compound. When they're separate ions, now we have to use that as a coefficient. So 2 potassiums, 1 chromate, 1 barium, and 2 nitrates are mixed together and they form this solid. Plus, we've still got potassium ions and nitrate ions floating around, and the same proportion, 2 potassiums and 2 nitrates. That's the complete ionic equation. But notice, where's the business happening? Where is the reaction actually happening? The reaction is happening between barium ions and chromate ions. The potassium and the nitrate ions are still in solution. They're just floating around happy as a lamb. Right? So those ions we call spectators. And if you remove the spectators from both sides of the equation, what you have left is a net ionic equation. This is where the business is happening. The barium ions are associating with the chromate ions to form this solid. That's what drives the reaction. Now, the value of a net ionic equation is, suppose we don't have barium nitrate on our shelf. We don't have potassium chromate on our shelf. If we have sodium chromate, if we have some other barium salt that's soluble, I can't think of a good one right now, then we can still carry out this reaction, because the only important ions are the barium and the chromate. The others are spectators. Okay? So that's how you sequence through a precipitation reaction, by writing the molecular equation, then the complete ionic equation, then cancel out the spectators, and you're left with a net ionic equation. Let's see. I need to take a short break. I'll be back in just a second. right. So here we have another example. Let me check something here. Check my slide set and see how far along we are. Okay. Yeah, we got a few more. Got a few more slides. See if I can finish by quitting time. Okay. This example asks us to write the correct molecular equation, the complete ionic equation, and the net ionic equation for this reaction, cobalt-2 chloride and sodium hydroxide. So first thing you do is erase all the old stuff. Right, and then write the reactants. They're both in solution as cobalt-2 chloride. Cobalt with a 2+ charge, and chloride with a -1 means we need 2 of them. They're in aqueous solution. And then we have sodium hydroxide. It's also an aqueous solution. Now, what does that yield? Well, sodium associates with chlorine. Okay. So we got sodium chloride, and you look it up, it is soluble. The other association is cobalt-2 hydroxide. Right. And that, when you look it up, you find that it's a solid. Let me check myself just to be sure. Cobalt and then hydroxide. Yes, it's insoluble. So we've written our compounds correctly and we've determined their phase. All right. Now we need to balance the equation. Now, you can, if I had more room, we could do the budgeting method, but these double replacement reactions are usually fairly simple to balance. We have 1 sodium, 1 sodium, 1 cobalt, 2 chlorides, and 2 hydroxides. So we need 2 chlorides. Now we need 2 sodiums, and that gives us 2 hydroxides. So that's balanced. All right. That is our complete molecular equation. Now, what do we do to make ions? Well, this one's soluble. So we have 1 cobalt 2+ ion in aqueous solution. We have 2 chlorides ions in aqueous solution. We have 2 sodiums in aqueous solution. And we have 2 hydroxides in aqueous solution. Okay. Let's see, we need to separate these right here like that. There we go. And that yields 2 sodiums in aqueous solution, 2 chlorides in aqueous solution, and 1, do that better, 1 cobalt hydroxide. Cobalt-2 hydroxide is solid. That's our complete ionic equation. Let's see, there's our molecular. We did that one already. And the complete ionic equation there. And just checking myself. Okay. With the rest of it. Yes. Okay. So now what we do is we find the spectators. The same in solution on both sides. We find one here, and here, and here, and here. And what's left over? What's left over is cobalt 2+ plus hydroxide. yields this compound. Precipitate. That's your net ionic equation. All right. Fairly simple. Just got to be methodical about it, step by step. Okay. Reactions that form water. What I showed you early on in this slide set was a reaction of an acid with a base. And when you react the acid with a base, you get the acids form these hydrogen ions. All of them do, right? Whether it's hydrochloric acid, nitric acid, sulfuric acid, whatever. They always form these hydrogen ions. They are in solution along with the anion that comes from that molecule. Okay. This is known as an Arrhenius base. The man's name, Arrhenius, proposed a definition for acids and bases way back in the 18th century, I think, maybe even earlier. But he said that an acid was any compound, when you put it in aqueous solution, forms hydrogen ions. Okay, so these are Arrhenius acids. Well, if that's an Arrhenius acid, what's an Arrhenius base? Well, let's see. Strong acids behave as strong electrolytes. So hydrochloric acid, hydrogen chloride in water dissociates completely. So we've got a lot of ions there that complete the circuit. Right? So that's a strong electrolyte. Bases, according to Arrhenius, are those molecules that can produce hydroxyls when they go into solution, like sodium hydroxide, potassium hydroxide. So now you've got the acids and the bases in solution. And these are also strong electrolytes because they completely dissociate. They form lots of ions to transmit the charge from one electrode to another. Okay. Now, when you put these together, what do they form? Well, let's take an example. Let's do that. I think it'll make more sense with a concrete example. So let's go back here to this example. HCl in aqueous solution plus sodium hydroxide in aqueous solution produces what? Well, the sodium can associate with the chloride. So we get sodium chloride in aqueous solution. And then the hydrogen ion can associate with the hydroxyl and produce water. This is a typical acid-base reaction. And by definition, an acid and a base produces a salt, not just table salt, any salt. It could be any cation, any anion from this reaction, and water. Okay, that's what you get from an acid-base reaction. You get a salt and you get water. And the net ionic equation, if we write this out complete, we would have this one plus this one plus sodium ions plus hydroxyl ions, like that, would produce sodium ions, chloride ions, and water. Okay. So if we write the net ionic equation from this reaction, we've got sodium on both sides, we've got chloride on both sides. Now the net equation is just hydrogen ions plus hydroxyl ions yields water. That's the net equation for all acid-base reactions. Okay? Okay, these are considered strong acids: hydrochloric acid, nitric acid, sulfuric acid. And when they go into solution, in aqueous solution, they produce hydrogen ions in abundance and anions. Now, for the hydrogen chloride, for the hydrochloric acid, it will make exclusively hydrogen ions and chloride ions in solution. For nitric acid, it will similarly dissociate into these ions. However, sulfuric acid has two hydrogens. So what happens with sulfuric acid is it's a strong acid for the first hydrogen. It produces one hydrogen plus this anion. Okay? Those are all strong acid dissociations. If you want that second ion from sulfuric acid, this is a weak acid. Okay? So this is the strong acid reaction. Now you can still get that hydrogen off of there in a reaction with a base. Right? It's not fixed. It will come off. But in solution, just these pure acids in solution, that's the reaction for each one, making it a strong acid. Similarly, a strong base dissociates into its cation and its hydroxyl ion. And remember, hydroxyls are polyatomic ions, OH minus. This is just reiterating. When you react an acid with a base, particularly strong acids with strong bases, you always get a salt and water. This is called an acid-base reaction. No matter what the source, hydrogen ions, hydroxyl ions react together to make water. That's the net equation. That's an acid-base reaction. So what's the net ionic equation for this reaction? It's kind of a trick question. You notice you've got an acid here with a hydrogen, and you've got a base here with the hydroxyls. When you put them together, you always get the same net ionic equation. Hydrogen ions plus hydroxyls yields water. Okay, when we transfer electrons, remember we said that was a driving force? There's a name for that reaction. It's called oxidation reduction. And the reason it's called oxidation reduction is oxidation defines loss of electron, reduction defines gain of electron, and they always occur together. Right? For our example here, magnesium is a metal. Metals like to give up their electrons. So magnesium transfers its electrons to oxygen. And now we have magnesium ions with the loss of electrons have been oxidized. Whereas oxygen has gained electrons, it has been reduced. And then you get the ionic association of cations with anions. And you get a magnesium oxide as your salt. The formation of the solid as a product. It's not always a solid, but in this case it is. Magnesium's a solid, oxygen's a gas, and you get a solid as a product. And these reactions always occur between metals and nonmetals. They can also occur between nonmetals and nonmetals, but I'm not so sure we're going to dig that deep into these reactions. Let's see. Okay, I misspoke earlier. I said stoichiometry was coming, not in this chapter. Stoichiometry is coming for the next exam. All right, so you don't have to deal with that. What now? We're talking about reactions and what drives the reactions, and then we're looking at the atomic level. Oxidation reduction reaction is always a transfer of electrons. Okay, there's the overall reaction, and this is the artist's depiction of what's happening. Okay. Let's see. Hold on just a second. Oh, I didn't put the slide in there for this one. Let me give you a way to remember whether you're talking about oxidation or reduction. There's an I forgot the term. It's not an acronym. It's a mnemonic device. Excuse me, a mnemonic device. So we write out oil rig, right? Oxidation is loss. So anytime something loses electrons, we say it is being oxidized. And reduction is gain. So anytime a substance is gaining electrons, it's being reduced. And they always occur together. In chemical reactions, you can't have one without the other. All right, so let's get back to the slide. Which of the following best describes what is happening in the following representation of an oxidation reduction reaction? All right. Aluminum gains 3 electrons and oxygen 2- loses these 3 electrons. Well, let's see. Oxygen, notice on either side of the reaction, oxygen doesn't change its charge. Oxygen's not involved. It's kind of like a spectator. Oxygen's there for charge balance, but it doesn't gain or lose electrons. So A cannot be it. Okay. Aluminum gains 3 electrons for each aluminum, and iron 3+ loses these electrons. No. Aluminum doesn't gain electrons. Aluminum loses electrons. Notice aluminum is going from a 0 charge to a 3+ charge. Aluminum loses electrons. Okay, that's better. Aluminum loses 3 electrons, but the oxygen still doesn't gain any electrons. All right, that doesn't work. Aluminum loses 3 electrons, yes. Iron 3+ gains these electrons. That is true. Iron goes from 3+ to 0. It had to gain 3 electrons for each iron. Aluminum loses 3 electrons. Okay, so if aluminum loses electrons, it is being oxidized. If iron 3+ gains electrons, it is being reduced. Now, this particular reaction, you may have seen YouTube videos of this one. This is the reaction for thermite. If you have powdered aluminum and iron 3 oxide or rust, and you light that, and it takes a lot of energy to get it started. You need a very strong torch. But once you get it started, the release of energy is massive. And what it produces is iron metal and aluminum oxide. So you may see this used on to weld railroad track together. They'll have the railroad track right up against, and then they'll cover it in this mixture, and then they'll also cover it in sand and a shroud, right? Because it's dangerous, right? Spark could fly off of that and set the woods on fire or hit somebody. So once that's safely contained, then they light it, and it produces iron, pure iron metal between those two rails and welds them together. All right. A metal and a non-metal reaction can always be assumed to be an oxidation reduction reaction, which involves electron transfer. Here's what we're saying. For our example, sodium, and which is a solid, and chlorine, which is a gas, right? And this is zero charge for both of them. Then what we do is we transfer electrons, like I showed you before, and we make sodium chloride, solid. So sodium is being oxidized. Chlorine is being reduced, because now it has gained electrons and sodium has lost electrons. Okay. One other clue: whenever you have a reaction in which, for instance, this one we showed you before, solid yields in aqueous solution plus hydrogen gas. Okay, notice that on this side, that is 0, but over here, it's a 2+. Whenever you see an element on one side of the equation or the other, and that element is part of a compound on the other side, then that is always an oxidation reduction reaction. Notice that in this case, chlorine didn't change. It was the hydrogen that changed from a +1 to a 0. So zinc was oxidized. Oxidation is loss. Hydrogen is reduced. Reduction is gain. Okay, they always occur in pairs. If two nonmetals undergo this reaction, we need a way to track the electrons, because nonmetals together are not charged. We can't assess their charge. So we need another way to do it. And that should be coming up. Okay, we've talked about formation of a solid, formation of water, transfer of electrons, and formation of a gas. This is a precipitation where a solid forms. We've looked at that one before. Notice this is also not an oxidation reduction reaction. Potassium still 2+, +1 on both sides. Nitrate is still intact with a -1 charge. Barium still 2+, and chromate is still 2-, right? There have been no electron transfers in this reaction. This is not an oxidation reduction. Okay. Let's see. All right. For this course, we're not going to go into nonmetals as oxidation reductions. It does happen, but we can't go into the depth required to assess that movement of electrons. So we're going to set that aside and just concentrate on types of reactions. So we've looked at precipitation reactions, acid-base reactions, where the net equation is hydrogen ions plus hydroxyls yields water. Oxidation reduction reactions, right? So here we have zero charge, and here we have a +1 charge and a -1 charge. So we know that something has happened. Plus, these are elements. Now they're in a compound. That's a dead giveaway. That is always an oxidation reduction. This is the reaction that I've been showing you on the board. Hydrochloric acid and zinc produces hydrogen gas and zinc chloride. Now, this is a combination of driving forces. We form a gas, yes, but we also transfer electrons. All right, so it's an oxidation reduction reaction and formation of a gas. This is often called a single replacement because we have one element here that's simply replacing the hydrogen. During this reaction, now the zinc is associated with chlorine and hydrogen is free. This flow chart might help a little bit. There are some other types of reactions, and these are operationally defined. A combustion reaction is by definition an oxidation reduction reaction, but it's special. It always involves elemental oxygen and produces energy. So in this case, we've got methane, CH4, and oxygen producing carbon dioxide and water. Now, they're all gases, so we can't say that the driving force here is formation of a gas, right? So we have to look to oxidation reduction as our driving force. So notice oxygen's an element here and it's in compounds over here. That's oxidation reduction every time. But this is combustion because oxygen, elemental oxygen is involved as a reactant. Other descriptive terms for reactions. When we have a combination reaction, we're forming compound from simpler materials, usually elements. So this is called a synthesis or a combination reaction. Both words are acceptable. And these are always oxidation reductions. When there's an element involved that becomes a compound, yes, that would be an oxidation reduction also. Decomposition is just the other way. Flip the reaction around and you get a decomposition. In this case, we're taking water and splitting it into hydrogen gas and oxygen gas. In this case, we're forming a gas, which could be considered a driving force for the reaction. Plus, it's an oxidation reduction reaction. That's also a driving force. All right. So if we look at these chemical reactions, we can say, okay, precipitation reactions are over here, acid-base reactions over there. We know the driving force here is the formation of a solid. The driving force here is formation of water. Oxidation reduction reactions are always driven by electron transfer, but we have some subcategories for that also. Combustion reaction is a special case. Synthesis reaction, special case. Decomposition reaction is a special case of oxidation reduction. We can also refer to oxidation reduction as a redox reaction. I think the only reason we say redox instead of oxrid is it just sounds better. Okay. So we're forming water. What type of reaction is this? Classified as a synthesis reaction. It's also a combustion. Oxygen's involved. And it's also oxidation reduction because we're transferring electrons to make the compound. So all of the above, all three are characteristic for this reaction. Oops. Okay. Let me stop this share. Okay. Your review document will give you practice identifying these types of reactions. We didn't go into all of them here as extra slides. Your review document will give you that practice. All right. So you get, several of them, lots of them, to give you a better feel for what type of reaction you're dealing with and how to classify them. That's the objective of chapter 7. What drives a reaction, how to classify them, how to identify precipitates. Okay, so it's 11 o'clock and we're done.